Quiet science journeys. A night ocean spreads in every direction, black water under a darker sky, and far away, a thin ring of pale light rests where sight begins to fail. From a distance, it looks clean and certain, like a boundary drawn with care. It feels like the kind of line that separates what is inside from what is not. The mind has been trained by objects. A cup has a lip. A book has a margin. A road has a shoulder. A photograph has a frame. When a clear edge appears, the mind quietly assigns an outside on the other side of it. On the sea, that instinct can be wrong. Nothing holds the water back at that ring. No seam is stitched into the surface. No wall rises from the dark. The line is only where the light has become too thin to read. Cosmology triggers the same instinct with even more force. A diagram shows a circle around a point and calls it the observable universe. A map of galaxies fades into a rim, and the eye treats the rim like the end of the place. The picture looks like a container, so the next thought arrives as if it were natural. If there is a rim, the mind supplies an outside, and then it supplies a second question, and then a third. The sentences borrow their grammar from rooms, and boxes, and bowls, and the assumptions hide inside the words. The shape of the question can tilt the answer before any physics has a chance to speak. But the universe is not a thing sitting inside a larger space the way a ship sits inside the sea. In cosmology, space is not a stage that exists first and then receives the universe as a guest. Space is part of the story itself, shaped by what exists in it and by how it has changed over time. Tonight the goal is to separate two ideas that are often tied together. The universe may have no edge in the sense of no physical border where space stops. Yet the universe can still have a horizon, a limit to what can be seen, known, or influenced. An edge is the end of a place. A horizon is the end of information that has had time to reach you. An edge would be a feature of space itself, a boundary you could imagine as a surface. A horizon is a feature of history, built from finite light speed and the age and expansion of the cosmos. That night, ocean offers a clean way to hold the difference. The sea can continue without a cliff, without a fence, without a final line in the water, and still your view ends somewhere. The ring is not a barrier, it is the limit of what your eyes can collect. This is the signature idea that will return again and again. Horizon is an information limit, not a wall. It does not declare that space ends there. It declares that beyond that boundary, the universe has not had a way to send you the details. It can help to see what changes when a horizon is mistaken for a wall. A wall invites a next step, a way around a ladder, a door, a beyond that feels like a neighboring room. A horizon does something quieter because it follows from time rather than from architecture. As the universe expands and as light travels at a finite speed, there are distances that cannot be connected in the same way. Some regions are too far for their light to have arrived, yet so they remain unseen in our past. Some regions are so far in an accelerating expansion that signals sent today will never arrive, even in the far future. These are horizons, and they are limits on communication, not limits on existence. They sort the universe by what can influence what, and by what can share information with what. They do not sort the universe into what is real and what is not. This is why maps of the cosmos can show a crisp boundary without implying a cosmic cliff. A map can end at the limit of a survey, the limit of a telescope, the limit of what the universe has had time to reveal, and a border on a map is often the end of data, not the end of land. In cosmology, the most famous border is a boundary of information, not a boundary of space. So the route tonight is simple and worth holding as a single arc. First, no edge because the universe does not need a physical rim like an object. Second, still a horizon because information has limits set by light speed and cosmic history. Third, beyond does not mean outside, because outside is a container word that may not apply. We will unpack why the word edge carries a hidden box and why that box bends every sentence that follows. We will see how a space can be finite without having a boundary in the same way a surface can close on itself without a seam. Then we will build the horizon not as a line in space, but as a record of what light and expansion allow. Along the way, the sea returns as a simple anchor because it keeps the categories honest. The line stays in your vision, yet nothing in the water corresponds to it as a structure, and that contrast is the point. In the same way, the observable universe has a boundary in our descriptions, yet nothing in space needs to stand there as a wall. The border is real as a limit on knowledge, and it is not real as a material edge. Horizon is an information limit, not a wall, and that single sentence keeps the rest of the story aligned. With that distinction in place, the title becomes less of a paradox and more of a guide. Why the universe has no edge but still has a horizon. The word edge carries a quiet box inside it, and that box shapes the way the question is asked. In ordinary life, an edge is the place where an object stops and something else begins. It is a boundary drawn inside a larger space. A table has an edge because it sits inside a room. A road has an edge because it is laid across a landscape that continues beyond it. A cup has a rim because there is air on one side and liquid on the other. These edges make sense because the objects are embedded in something larger. They occupy space, but they do not define space itself. The edge belongs to the object, not to the arena that holds it. Over time, the mind learns this pattern so well that it feels universal. When a line appears, the mind expects a container. When a boundary is drawn, the next thought is what lies outside. That habit follows us into cosmology with almost no resistance. When we see a diagram of the universe as a circle, we read it like a bowl. When a map fades at the rim, we treat the fade like a cliff, and the picture looks familiar, so the assumption feels harmless. But the universe is not an object placed inside a larger space. There is no external room that holds it, no surrounding emptiness that exists first and then receives it. In modern cosmology, space is not the box. Space is part of what is being described. This is the first quiet error behind the question. Does the universe have an edge? The word edge assumes a container that has not been justified. It asks for the end of space, as if space were a thing with a surface. Once that assumption slips in, every answer begins to tilt. What is that outside made of? Does it have its own laws, its own time, its own dimensions? If there is space beyond the universe, why is that space not part of the universe as well? The question multiplies instead of resolving because the starting picture was borrowed from rooms. Physics avoids this trap by refusing to smuggle the container in at the start. Instead of asking where space ends, it asks how space behaves. Instead of looking for a wall, it looks for relationships, distances, and histories. The geometry comes first, not the image of an inside and an outside. The most reliable questions in cosmology tend to be questions about what can connect to what. This is where everyday language begins to mislead. Words like inside and outside work well for houses and oceans. They work poorly for the totality of space and time, and when applied too literally, they generate questions that feel deep but have no clear target. The night ocean keeps this clear. Standing on the water's surface, you can point to a line where vision stops, and you can feel the temptation to treat it as the end of the sea. But the limit of sight is not a property of the water, it is a property of light and distance and the sensitivity of your eyes. The same confusion appears when we talk about the edge of the observable universe. The word observable already signals a limit tied to measurement, yet the mind still wants to turn that limit into a physical boundary because the circle on the page looks like a border. In cosmology, many limits arise without any edge at all. There are limits set by how fast signals travel. There are limits set by how long the universe has existed. There are limits set by how space itself has expanded over time. None of these require a surface where space stops. They require only a history and a speed. They are limits of connection, not limits of existence. The danger of the word edge is that it collapses all limits into one image. It treats every boundary as if it were a wall, and once that wall is imagined, the mind begins to search for doors and ladders. Physics, meanwhile, is talking about clocks and light. This is why cosmologists rarely say edge when they are being precise. They speak of horizons of curvature, of topology, of causal structure. Each of these words points to a different kind of limit, and none of them require space to terminate. A horizon in particular does not behave like an edge. You do not arrive at it and look over. It is not a place you reach after traveling far enough. It is a boundary, defined by what has had time to connect. Holding on to the box makes horizons feel unsatisfying. If there is no wall, the mind asks, what stops things from falling out? But falling out only makes sense when outside is already real, in the way a room is outside a cabinet. Those directions belong to containers, not to space-time. Once the container is released, a different picture becomes possible. Space can be finite without being fenced. It can be limited in what it reveals without being cut off. The absence of an edge stops being a problem that needs solving. This does not make the universe vague or mystical. On the contrary, it makes its limits sharper because horizons can be calculated, modeled, and tested against data, while a wall at the end of space cannot. The habit of the box is strong because it is useful everywhere else. It helps us navigate houses, cities, and landscapes. But the universe is not one more object among others. It is the framework within which objects appear at all. So before asking where the universe ends, it helps to pause on the word end. Ends belong to things that sit in something larger. If there is no larger container, the question has already drifted. The edge was assumed before it was earned. Letting go of that assumption does not remove limits from the story. It clears the way to understand them properly. What remains are horizons, not walls, limits of information, not borders of space. With that distinction in place, the next step becomes possible. A universe without an edge does not have to be infinite. A space without a boundary does not have to stretch forever, and those ideas belong to geometry, not to boxes. Space can have no edge without being infinite, and that sentence sounds strange only because the mind keeps reaching for a box. In a box, no edge would seem to mean the box goes on forever, but geometry allows another option. Begin with a surface that is familiar and easy to picture. Take the surface of a sphere, not the solid ball, just the skin, and notice what it gives you. It has a finite area, yet it has no boundary line where the surface stops. If you walk on that surface, you never meet a rim. You can keep going in one direction and return to where you started, and no special point is marked as the edge. There is no place where the surface ends and an outside begins. This is not a trick of language, it is a property of the shape. The surface is finite, but it is unbounded, and it is closed without needing a border. The key is to separate two ideas that everyday speech blends together. Finite means there is a limited amount of extent, like a limited area or volume. Bounded means there is a boundary, a cut line, an edge, and a thing can be finite and still unbounded. On the sphere, the lack of an edge does not come from hiding the edge. Somewhere it comes from the way the surface is connected to itself. That is the geometric lesson, and it carries into cosmology. When people ask for the edge of the universe, they usually imagine a boundary in three-dimensional space, a place where you could arrive and look over. The sphere teaches a different possibility. because a space can be connected in a way that has no boundary. In principle, a three-dimensional space can be closed on itself the way the two-dimensional surface of the sphere is closed. You could travel far enough in some direction and in a suitable geometry return without ever crossing an edge. No wall is required for that kind of closure. This does not mean the universe must be shaped like a simple three-dimensional sphere. Real cosmology allows many possibilities, and observations place strong limits on which ones can describe our world. The point here is more basic. An edge is not demanded by logic. It also does not mean that space must be finite. A space can be infinite and still have no boundary, and the lesson is that edge and infinite are not the same question. You can remove the edge without committing to infinity. In everyday life, we rarely meet unbounded finite spaces. Rooms end at walls, roads end at junctions, fields end at fences. So the intuition becomes finite, means enclosed. Geometry breaks that habit gently, and it does so without changing what the words mean, only by showing how they can separate. When cosmology uses the phrase no edge, it is speaking in that geometric sense. It is not claiming there is nothing beyond a certain distance. It is claiming that space is not like a sheet with a torn border. There may be no boundary surface at all. This is why the question, what is outside the universe, can be the wrong kind of question. Outside assumes the universe is an object in a larger container, but if space is the arena itself, the phrase outside has no clear role. It is like asking, what is north of the North Pole? On a globe, north is not blocked by a wall. It stops being a direction that continues, and the words still exist, but the target does not. That is the kind of shift that happens when topology matters, and topology is the study of how a space is connected. Topology is not about the local feel of flatness or curvature in one neighborhood. It is about global structure, about whether paths can wrap around, and it tells you whether a boundary exists as a feature of the space. This is a quiet reason why the universe can lack an edge, not because it is protected by something, but because the geometry of space might not include a boundary in the first place. Hold that thought against the night ocean again. The sea does not need a fence to continue, and your view ends at a horizon of faint light, but the water need not. A limit in what you can see is not proof of an edge in what exists, and the same logic applies to the observable universe. No edge is a statement about geometry, not about the reach of your instruments. It is compatible with a universe that is finite, and it is also compatible with a universe that is infinite. What matters is that the absence of a boundary does not force any single answer about size. Once the box is gone, the next question changes shape. It is no longer where is the rim of space, as if space were a container with a lip. It becomes what limits the information we can receive, and that is where horizons enter. Horizons explain why a universe can have no edge and still show a boundary in our diagrams. The boundary is not a place where space stops. It is a place where information stops arriving. That is the difference between a wall and a horizon, and it is the difference that keeps the rest of the story aligned. So this part closes with a simple shift in category. No edge is a geometric claim about boundaries, not a claim about how far you can see. The limits we encounter in observation come from light and time and expansion, and those limits do not require space to end. With that in place, a map with a rim becomes less mysterious. The rim is not the end of the universe, it is the end of the data. From here, the route can move from geometry to observation, from no edge to still a horizon. When cosmologists draw a map of the universe, it almost always has a rim, and that rim looks deliberate. Galaxies, thin-out colors fade, and the picture ends in a clean circle, so it's easy to forget that the map is not the territory. That boundary is not chosen because space ends there. It appears because observation has limits, and a map can only include what has had time to send information to the observer. Beyond that, the page goes blank, not because reality disappears, but because the messages have not arrived. This is where the phrase observable universe does its quiet work. Observable does not mean small or special, it means connected by signals that have reached us. The boundary marks the reach of information, not the reach of space. Two simple facts are enough to create such a boundary. Signals do not travel infinitely fast, and the universe has existed for a finite amount of time. Together, those facts guarantee a horizon even before any complicated physics enters the story. Light carries nearly all of the information we use to map the cosmos. It moves at a fixed speed, so no matter how powerful a telescope becomes, it cannot receive light that has not yet arrived. Time sets the limit before technology ever has a chance to help. If the universe were infinitely old, this would not matter in the same way. Light from arbitrarily distant regions would have had time to reach us, and the map could, in principle, extend without a rim. But the universe has a history, and cosmic time has been counting forward. Because of that history, there are distances from which light simply has not had enough time to travel. Those regions are not hidden by dust or darkness, they are hidden by time itself. The map ends where the light trail ends, and that ending is a fact about our past light cone. This is where the night ocean remains a reliable guide. Standing at the water's surface, the horizon appears as a sharp line, yet nothing in the sea corresponds to that line as a structure. It is the place where light reflected toward you becomes too weak to register, and the surface can continue without interruption beyond it. Cosmic maps work the same way. The rim marks where signals become unavailable, not where space changes character, and there is no cosmic shoreline at that distance. There is only the limit of what can be known from here at this moment by signals that have had time to arrive. You can see this by imagining what happens as the universe ages. As time passes, more light arrives from farther regions, so the observable past grows. The boundary in our maps moves outward without requiring space to unfold beyond an edge, because the change is in what has reached us, not in what exists. In that sense, the observable universe is a moving concept. It is tied to the age of the universe and to the kinds of signals we can detect, and it expands as time passes because more information becomes available. The universe does not need to add new territory for the map to gain new detail. This is the second appearance of the signature idea. The boundary of the map is where data stops, not where space stops, and horizon is an information limit, not a wall. The circle belongs to our knowledge, not to the universe itself. It is important not to confuse this with a statement about certainty. Beyond the observable region, physics does not declare ignorance of everything, it declares limits on direct evidence. The difference matters because cosmology can still reason beyond the map, but it does so by inference, not by direct observation. Cosmological models extend beyond the observed region by assuming consistency. They test whether the laws measured here apply elsewhere, and they check whether patterns break or repeat. But these extensions remain distinct from the raw boundary drawn by light. The raw boundary is not a guess, it is the reach of signals. That reach is set by history. Light left distant regions long ago, but not long enough ago to reach us yet, and in many cases, it will arrive in the future. The map will grow because the universe has more time to send us its record. But not every message is guaranteed to arrive because expansion is not just a background detail. The universe has been expanding while light travels, so the path a signal must cross can change beneath it. This is why cosmology distinguishes between different kinds of horizons, because not all limits are the same. For now, it is enough to hold on to the simplest boundary. Observable means the signal has arrived and the rim appears where signals have not yet arrived. That is why every map must end somewhere even if space does not. The mistake comes from treating the picture as if it were an object. A circle drawn on paper invites thoughts of inside and outside, and the mind tries to give the rim the same meaning it gives a fence. But a map is a record, not a container, and its borders belong to the record. Seen this way, the rim of the observable universe becomes less dramatic. It is not a cliff in reality, it is the place where the story written by light pauses. The rest of the page is blank because the ink has not arrived, not because the universe has stopped. This prepares the ground for the next idea. If there is a limit to what has already reached us, there is also a limit to what ever will, and time can close doors as well as open them. The future-facing boundary is another horizon, built from the same simple facts, but shaped more strongly by the way expansion behaves. For now, the map can keep its circle without turning it into a wall. The universe does not need an edge to produce a boundary in our diagrams, and the boundary is a consequence of light and history. Space itself is not asked to stop, only our information's is. Particle horizon marks the farthest distance from which light has had time to reach us. It is not defined by a wall in space, it is defined by a clock, specifically by how long the universe has existed. Every signal carries a timestamp because light does not arrive instantly. It moves at a finite speed, carrying information forward through time, and that simple fact already builds a limit. If the universe has a finite age, then there is a maximum amount of travel time available to any message. Imagine rewinding the history of the universe. At earlier times, space was smaller and denser, and light was emitted from many regions as expansion unfolded. Some of that light has already reached us, and some of it is still on its way, not because it is trapped, but because it has not had enough time. The particle horizon is the boundary traced by the oldest light that has reached us so far. It separates what we can observe in the past from what remains unobserved, and this separation is not about direction, it is about duration. The horizon is a statement about which travel times have been completed. Light from beyond the particle horizon has not been blocked or destroyed. It simply has not had enough time to arrive, and the universe has not existed long enough for that journey to finish. Time, not distance alone, sets the limit. This is where intuition can drift, because distance by itself does not define the horizon. What matters is distance combined with the history of expansion, since space has been stretching while light has been traveling. The distance a signal must cross is not fixed the way it would be in a static world. Because of that, stretching the path light follows is not a straight line through unchanging space. The distance it must cross changes while it moves, yet the principle remains simple. Finite time and finite speed imply a maximum reach. This is the first math light anchor. Time multiplied by a finite speed produces a limit, and you do not need numbers to feel it. You only need to accept that neither quantity is infinite, and then the existence of a boundary of arrival becomes unavoidable. The particle horizon is often drawn as a sphere around the observer. That picture can be useful, but it can also mislead because the sphere is not a shell you could ever touch. It is a record of which light paths have completed their journey, a boundary in what has arrived, not a surface in space. If you were to travel outward through space, you would not encounter the particle horizon as a structure. You would not cross a surface and enter a new region because the horizon is not waiting for you at some fixed distance. It is defined only relative to a specific observer and a specific time. This makes the particle horizon different from borders we know. A border remains even if no one is present to see it, but the particle horizon exists only because there is a here and a now. Change the observer or the moment and the horizon changes, because it is tied to which signals have had time to arrive. Return again to the night ocean. The ring of faint light marks how far illumination has reached your eyes, and it does not exist as a feature of the water. If you wait or if the light source grows brighter, the ring shifts and the sea itself does not need to change at all. The particle horizon behaves in the same way. As the universe ages, more light has time to arrive, so the observable past grows larger. The horizon moves without any change in the underlying space, because what changes is the amount of time available for travel. This is why the particle horizon is sometimes described as the edge of the observable universe. The phrase is convenient, but it must be handled carefully, because edge here does not mean boundary of space. It means boundary of past visibility, the farthest past from which light has reached us. The light we see from near the particle horizon is extremely old. It was emitted when the universe was young, and by observing it, we look back across most of cosmic history. The horizon is a time machine, not a wall, because it organizes what we can know by travel time. One of the most important examples of this is the cosmic microwave background. That radiation comes from a time when the universe first became transparent to light, and it arrives from nearly the same distance in every direction. It sits close to the particle horizon because it is among the oldest electromagnetic signals we can observe. Yet even here the horizon does not enclose us like a shell. The radiation does not mark the edge of space, it marks the edge of a particular era of observation. Earlier times remain beyond reach, not beyond existence, because the universe was opaque to light before that transition. This distinction prevents a common mistake. It is tempting to imagine the particle horizon as a place where something dramatic happens, but nothing special occurs there locally. Regions beyond it behave like regions here, forming stars and evolving under the same physical laws as far as our models indicate. They are simply too far back in time for their light to have reached us yet. In that sense, the horizon separates arrival from non-arrival, not reality from non-reality. It is a boundary in information, not a boundary in space. The particle horizon also reminds us that knowledge grows with time. What is unobservable today may become observable tomorrow, not because space changes, but because travel time accumulates. As cosmic time advances, new regions enter our past light cone, and the map fills in without any need for an edge. At the same time, the horizon remains a true limit at any given moment. There are facts about the universe that cannot yet be observed, and no improvement in technology can overcome a lack of time. The particle horizon is a constraint set by the universe's age. Seen this way, the horizon fits cleanly into the larger route. No edge means no place where space itself stops, and particle horizon means there is a limit to the past we can observe. Horizon is an information limit, not a wall, and the particle horizon says nothing about where the universe ends, only about which messages have arrived. This prepares the next step. If there is a horizon set by the past, there can also be a horizon set by the future. Some signals have not arrived yet, and others never will, and that future-facing limit is shaped not just by time, but by the behavior of expansion itself. Event horizon is not about how far we have already seen. It is about how far we will ever be able to exchange messages with. It turns the horizon from a record of the past into a boundary of the future, and its meaning depends on how expansion behaves over time. In an expanding universe, distances between far regions can grow even when nothing locally is moving through space. Galaxies can remain at rest with respect to their local surroundings, while the space between them stretches. This is not a race through space faster than light. It is the scale of space itself changing. Now, aim that idea toward communication. A signal has to cross a distance before it can matter to you, and if that distance grows too quickly, while the signal travels, the message can be left behind. In that case, the signal is not blocked, it is simply never delivered. This is the core of an event horizon in cosmology. There can be regions so distant that light sent today will never reach us, not even in the far future. The reason is not that light slows down. The reason is that expansion can keep adding distance faster than the message can remove it. The word never sounds absolute, so it deserves careful handling. Never here is not a dramatic claim about existence. It is a claim about causal contact, about whether one region can affect another. The horizon is drawn by reach, not by reality. Return to the night ocean, but shift the direction of time. Earlier, the ring of pale light marked how far illumination had already reached your eyes. Now imagine which ripples on the surface will ever reach you at all, because some disturbances spread outward but fade before arriving. An event horizon works in this forward-facing way. It separates events that can influence us in the future from those that cannot, and it is not a place you arrive at. It is a limit on which futures can connect. This is where accelerated expansion becomes decisive. If expansion slows down, enough distant signals can eventually catch up. If expansion speeds up, the opposite can happen, and some regions become permanently out of reach. Observations indicate that cosmic expansion is accelerating. The details involve models and parameters, but the qualitative result is enough here. When acceleration persists, an event horizon appears a horizon of influence rather than a horizon of past visibility. You can picture it as a fading of possible contact. A galaxy can exist beyond that boundary, forming stars and evolving normally, but no light it emits today will ever arrive here. Its future becomes disconnected from ours, even though its existence does not. This is another appearance of the signature idea. Horizon is an information limit, not a wall, and the event horizon does not say that space ends there. It says that beyond that boundary, there is no future exchange of information with us. It is easy to misread this as a statement about what exists. It is not a claim that regions beyond the event horizon are unreal, and it is not a claim that physics breaks beyond it. It is a claim about what can ever enter our causal past. A useful way to frame it is to think in terms of events rather than places. Some events can eventually send signals that reach us, and other events cannot, no matter how long we wait. The event horizon separates these two classes, and it does so by the structure of space-time, not by a physical barrier. This horizon is not a fixed object floating in space. It depends on the observer and on cosmic time, because it is defined relative to what that observer can ever receive. It is described using the expansion history of the universe, not by drawing a wall and assigning it a distance. If you imagine traveling toward the event horizon, the concept would shift with you. It would not stand still like a wall, because its meaning continues to depend on the global expansion history. It is a relationship, not a location. This is why horizon language replaces the box so effectively. Instead of dividing space into inside and outside, it divides events by connectivity. It asks who can influence whom, and it draws limits with time, not fences. This perspective also explains why cosmic futures can become lonely. As time passes, more galaxies cross beyond our event horizon, and their future signals will not reach us. Even if their past light remains visible for a time, their future influence fades away. Visibility and influence are not the same. Light emitted long ago can still arrive, while messages sent in the future may fail, and horizons separate these ideas cleanly. The ocean image holds the contrast. The ring you see is about what reaches you now, and the event horizon is about what will reach you ever. This is also why cosmology treats horizons as information boundaries. They sort the universe by causal contact, and they define what can be connected by signals over time. They do not declare edges in space, and they do not imply that space stops. With the event horizon in place, the story has two different limits. One limit is about the past, what has already reached us, and the other is about the future, what will ever reach us. Both are about information and causality, not about walls. This prepares the next boundary that is often confused for an edge. It involves the speed of light directly, it looks precise and authoritative, and it is called the Hubble radius. It will seem like a hard rim at first, but it is a different kind of scale. The Hubble radius is the distance where cosmic expansion creates the strongest illusion of an edge. It appears whenever speed and distance are discussed in the same sentence, and because light has a special status, the idea feels decisive. But this boundary is not what it first seems. To understand it, begin with expansion itself. Galaxies are not flying through space away from us like debris from an explosion. Instead, the space between galaxies is stretching and distances grow, even when objects remain locally at rest. This stretching can be described as a recession speed. Farther galaxies recede faster, not because they move through space faster, but because more space lies between us and them. The expansion is spread across distance, so the rate of separation grows with distance. At some distance, this recession speed equals the speed of light. That distance is called the Hubble radius, and on diagrams, it often appears as a clean circle. It looks like a boundary that nothing should cross, and it is easy to treat it like a hard rim. At first glance, this sounds like a limit on signals. If something is receding at the speed of light, it feels as though light from beyond it should never arrive. The phrase faster than light seems to seal the case, and this is where intuition quietly breaks. The key mistake is treating recession speed like ordinary motion. No galaxy is locally outrunning a beam of light next to it, because locally, light still moves faster than any object through its nearby space. What changes is the space the light must cross, not the local rule for motion. A useful image is a measuring tape being pulled apart. Marks on the tape do not slide along the tape itself, yet the distance between them grows because the tape stretches. Expansion works in this way, and it separates motion through space from the expansion of space. This is the second math light anchor. The ruler itself is changing length and motion through space, and the expansion of space are different effects. Confusing them turns a scale into a wall, and that is the source of the Hubble radius illusion. Because of this, the Hubble radius is not a true horizon. Light emitted from beyond it can still reach us under the right conditions, and in the past, many galaxies we see today were once beyond the Hubble radius. Their light arrived because the expansion rate changed over time. The Hubble radius depends on how fast the universe is expanding at a given moment. It is tied to the expansion rate, not to the full history of the universe, so as that rate evolves, the radius changes. A real wall would not behave this way, and a true horizon would be defined by arrival over all time, not by a snapshot. This is why the Hubble radius is sometimes called a kinematic boundary. It describes a balance of rates at an instant where the recession speed equals the speed of light. It does not describe a permanent limit on communication. It is a snapshot, not a destiny. If expansion slows down, the Hubble radius grows. Regions that were once receding faster than light can come back into causal contact, and light that was struggling can make progress. The boundary moves without anything physical crossing it, because it is defined by the expansion rate, not by an object. If expansion speeds up, the Hubble radius can shrink. Regions that were once within it can slip beyond it, and again, nothing dramatic happens locally. No surface is crossed, no barrier is struck. Because the radius is not a structure in space, it is a scale derived from the current expansion. This behavior is very different from that of an event horizon. An event horizon is defined by what can ever reach us, while the Hubble radius says nothing about the ultimate fate of signals. It only describes the present balance of expansion and light, and the two should not be confused. Diagrams can make this confusion worse. A circle labelled with a precise formula looks authoritative, and it invites the eye to treat it like a boundary line. The label hides the time dependence, and the visual suggests a fence where there is only a changing scale. Return briefly to the ocean image, but use it carefully. Imagine waves spreading while the surface itself stretches outward, so a crest can still move relative to nearby water, while the distance it must cross changes beneath it. The Hubble radius is like a line drawn from the current stretch rate, not a statement about which waves will arrive. This is why the Hubble radius is useful, but dangerous. It is useful for describing cosmic dynamics, and it is dangerous when mistaken for an edge. When scale becomes barrier, the box returns under a new name. In the early universe, the expansion rate was very different. The Hubble radius was much smaller, and light from regions that were once far beyond it is reaching us today. This is one reason the cosmic microwave background is visible, because its photons were emitted when expansion was strong, yet they still arrived as the expansion history evolved. Seen this way, the Hubble radius becomes a diagnostic tool. It helps cosmologists track how expansion changes, and it helps organize which scales behave in which way. It does not mark where space ends, it marks how fast space is stretching right now. This clears away one of the most persistent confusions. The universe does not end where recession speed equals the speed of light, and space does not tear or break there. The concept of an edge does not suddenly apply, only a convenient scale does. With this distinction in place, the landscape becomes simpler again. No edge refers to the absence of a boundary in space itself. Particle and event horizons refer to limits set by time and expansion. And the Hubble radius is a useful kinematic scale, not a wall. Now, one famous cosmic image can be placed properly. There is a spherical boundary we see in every direction, and it looks like a shell around us, but it is neither the Hubble radius nor a wall. That boundary comes from light released when the universe was very young, and it is called the cosmic microwave background. The cosmic microwave background is often described as a picture of the early universe, and that phrase is useful as long as it is handled carefully. It is not a photograph taken from the outside, it is light that has been travelling toward us for most of cosmic history. In every direction we look, this radiation arrives from nearly the same distance. It forms a spherical surface around the observer, and that symmetry makes it tempting to imagine a shell enclosing us. But the shell is not a structure in space, it is a boundary in time. The microwave background comes from a specific moment in cosmic history. Early on, the universe was hot and dense, filled with charged particles that scattered light constantly. Photons could not travel freely, so space was opaque to radiation. As the universe expanded and cooled, a transition occurred. Electrons combined with nuclei to form neutral atoms, and light was suddenly able to move long distances without scattering. The universe became transparent, and radiation released at that moment began its long journey. Those photons have been traveling ever since. What we see today as the microwave background is that ancient light arriving now carrying information from a time, not from a wall. The signal is a message from an era when the universe first allowed light to travel freely. This is why the background appears as a sphere. We are receiving light that was emitted at roughly the same cosmic time in every direction, so the travel time is similar and the distance is similar. The sphere is drawn by time and light travel not by space ending. It helps to connect this to the particle horizon. The microwave background lies close to the farthest distance from which light has reached us so far, and it represents the oldest electromagnetic signal we can observe. Beyond it, earlier times remain hidden from direct view, not because nothing existed, but because light could not travel freely then. That distinction matters. Before transparency, information was present but trapped in constant scattering, so it could not arrive to us as a clean signal. The horizon here is an observational boundary set by the state of the universe, not a boundary of space. The night ocean remains a useful anchor again. The ring of faint light marks how far illumination reaches your eyes, and it does not mark where the water begins or ends. The microwave background plays the same role on a cosmic scale. It marks where electromagnetic information about the early universe becomes available. The background also shows why horizons are not walls. Nothing special happens locally at the distance from which this light was emitted, and observers there would not see a boundary around themselves. They would see their own sky filled with similar radiation, because every observer has their own version of this sphere. Each one is centered on the observer, not on a special place in the universe. That alone rules out the idea of a physical shell, because a real wall could not be centered everywhere. The sphere is a feature of observation, not an object hanging in space. The microwave background is sometimes called the edge of the observable universe. The phrase can be convenient, but only if edge is understood as a limit on what electromagnetic signals can show us from the past. It is not the edge of space, it is the edge of a particular kind of observation. There are other messengers besides light. In principle, gravitational waves and neutrinos can carry information from earlier times because they interact differently with matter. Each messenger has its own horizon, set by how it travels and how the universe evolves, and none of them require a boundary where space stops. The microwave background also reveals something else that matters for the story beyond our horizon. The universe on large scales appears remarkably uniform, and the radiation looks nearly the same in every direction. Small variations carry a great deal of information because they encode tiny differences in density that later grew into galaxies and clusters. Those variations support the idea that the laws we measure here apply far away. They do not prove what lies beyond our view, but they constrain the possibilities, and they give cosmology reasons to treat the unseen region as connected to the same physical story. The horizon limits data, not reasoning, grounded in data. At the same time, it is crucial to keep the categories separate. The microwave background is a boundary in time, not in space, and it marks when light first traveled freely, not where space ends. Treating it as a shell reintroduces the box in disguise. When diagrams show a glowing sphere around the observer, they compress history into geometry. That compression is useful for visualization, but it can quietly revive the idea of an enclosing surface. The reality is more subtle because the sphere exists in space-time as the set of events from which photons are reaching us now. Change the time of observation, and the sphere changes. A wall would not behave this way, and that time dependence is a clue to what the sphere really means. It is a timestamp on our past light cone. This also clarifies why the background does not conflict with no edge. A universe can have no spatial boundary and still present a spherical horizon of observation, because the two ideas address different questions. One is about geometry, the other is about history. As the universe continues to age, the microwave background will grow colder and fainter, because its photons will stretch to longer wavelengths as space expands. It will remain part of our past light cone, but it will not turn into a wall, it will only become harder to detect. The background therefore fits neatly into the root of this story. No edge describes the absence of a boundary in space itself. Horizons describe the limits set by light and time, and the microwave background is one of the clearest examples. It looks like a shell, but behaves like an era, and its boundary is informational. With that in place, the idea of beyond becomes easier to handle. Beyond the microwave background does not mean outside the universe, it means earlier than the light we can see. That distinction will matter even more as we move on. Beyond the horizon is often described with a single word outside, and that word carries more baggage than it seems. It suggests a place beyond a boundary, like land beyond a fence, and in cosmology, that suggestion can quietly mislead. There are at least three different ideas that tend to collapse into one. Beyond the observable region, beyond future causal contact, and outside the universe as a place you could point to. The first two are meaningful in physics, and the third is often a category error. Beyond the observable region simply means beyond what light has reached us from so far. It is a statement about our past light cone, and it says nothing about what exists there. It only says that information from those regions has not yet arrived. Beyond future causal contact refers to the event horizon. It marks regions whose future signals will never reach us, and this is a statement about communication and influence. It does not claim that those regions cease to exist. It claims that they cannot affect us in the future. Outside the universe, by contrast, treats the universe as an object in a container. It assumes a surrounding space that holds it, and if space itself is part of the universe, that assumption has no clear meaning. The question dissolves rather than waiting for an answer, because outside has no physical target in the way it does for rooms. The night ocean keeps this distinction steady. The horizon marks where light reflected toward you fades away, and beyond that line, the water continues. There is no outside of the sea, implied by the horizon, only a limit on what can be seen from where you stand. Cosmic horizons work the same way. They mark where information stops arriving, and they do not mark where space stops existing. The beyond is still part of the same space-time, described beyond our direct access. This has an important consequence for how cosmologists reason. Even though we cannot observe beyond the horizon directly, we can still infer properties by looking for consistency, symmetry, and continuity. We test whether models that fit here also fit everywhere, and we check whether large-scale patterns suggest a shared history. The uniformity of the cosmic microwave background plays a key role. It suggests that regions far apart share similar conditions, and that similarity supports the idea that what lies beyond our view is not exotic by default. The horizon limits evidence, not the existence of laws, and it does not force a sharp change just beyond the boundary. At the same time, inference has boundaries. Physics does not claim detailed knowledge of unobservable regions, it claims constrained possibilities. Beyond the horizon is not a blank slate, but it is not a detailed map, either, because direct data does not reach us from there. This balance is easy to lose when the word outside sneaks in. Outside invites pictures of walls and containers, and it pushes the mind toward geography when the issue is causality. The result is a question that physics did not ask, and that physics may not need. A useful comparison is geographic language. There was a time when beyond the ocean horizon meant unknown, and it did not mean non-existent. As ships traveled farther, the horizon moved without revealing an edge to the earth, and the error was not in the sea, but in the assumption that sight defines borders. In cosmology, travel does not work the same way. You cannot sail past the horizon of the universe because the horizon is tied to light, and time not to motion through space. But the logic of unknown versus non-existent still applies, and that logic helps keep the picture honest. Beyond the horizon is therefore not a separate realm. It is the same universe described beyond our observational and causal reach, and its physics is constrained by what we observe here. The details remain inaccessible by direct measurement, but the story does not require a wall. This is why cosmological models extend smoothly beyond the observable region. They do not insert a boundary condition labeled end of space, they extend equations and symmetries. They test whether those extensions remain consistent with what we see, and they remain careful about what is inference and what is observation. In some models, space is finite and closed. In others, it is infinite and open, and both possibilities can include horizons. Neither requires an outside, because horizons are limits of information not limits of existence. Language matters because it shapes intuition. When outside is treated as a place, curiosity turns into a demand for walls. When beyond is treated as a limit of information, the picture becomes clearer and the universe does not need a frame to have horizons. This also helps explain why questions about what lies beyond are not meaningless. They are meaningful when framed in terms of physics, such as what curvature is allowed, beyond what expansion behavior is implied beyond, and what kinds of initial conditions remain consistent with what we see. These are questions about models and constraints, not about rooms. They become confused only when framed in terms of containers. What room is the universe in what surrounds it, and what lies beyond the edge, as if the universe were a thing with a surface? Those questions assume a structure that has not been established. The distinction is subtle but important. Physics answers questions about relations, laws, and limits, and it does not always answer questions about imagined places. Horizons belong to the first category, and outside often belongs to the second. Beyond the horizon, then, is not outside the universe. It is outside our observational and causal reach, and those are precise statements. They do not require a wall, and they do not imply an edge. Holding on to this distinction prepares the final pieces of the route. If beyond does not mean outside, then finiteness and infinity must be reconsidered carefully. Curvature and topology enter next, and they describe how space is connected, not where it ends. Curvature and topology answer different questions, and mixing them creates confusion. Curvature describes how space bends locally, and topology describes how space is connected globally. One does not determine the other, and that separation matters for the question of finiteness. Curvature can be measured by observing how light and matter move. On large scales, measurements show that space is very close to flat, meaning the geometry we infer is consistent with only very small curvature. It is tempting to turn that result into a verdict, because flat feels like infinite and curved feels like finite. That shortcut is not reliable. A space can be nearly flat and still be finite, because flatness measured over a limited region does not fix the global shape. It tells you how geometry behaves locally, not how paths connect far away, and topology remains free. This is the third math light anchor. Near zero is not the same as zero, especially when measurements are made over a finite range. Small curvature can hide a closed structure that is simply too large to reveal itself within the region we can observe. The surface of the Earth offers a familiar analogy. On small scales, it feels flat. Roads look straight and horizons look level, but the curvature becomes clear only when distances grow large. Local measurements can be consistent with flatness, even on a curved global surface, as long as the region is small compared to the full size. In cosmology, the situation is similar, but more abstract. We measure curvature within the observable region, and that region is vast, but it is still limited by horizons. What lies beyond can change the global picture, and even within what we can observe, a very large closed universe can look almost perfectly flat. A universe could be finite without having an edge. It could wrap around in a way that connects distant regions so that travel would never encounter a rim. No boundary surface would appear anywhere, because closure would be a feature of connection, not a feature of a wall. A universe could also be infinite and unbounded. Space could extend without limit in every direction, and again, no edge would appear. Infinity and no edge are compatible, and finiteness and no edge are compatible, so the presence or absence of an edge does not decide the question. What curvature does not do is force a boundary. Positive curvature does not require an edge. Zero. Curvature does not guarantee infinity, and negative curvature does not demand openness. Curvature is a local geometric property, and topology is a global property of connection. Topology asks whether paths eventually reconnect or continue forever. It asks whether space closes on itself, and it does not care how gently or sharply space bends locally. This is where the idea of a container fails completely, because a container has walls, while topology describes connections without walls. The ocean image can be used carefully here as well. As you look outward across the sea, the horizon cuts off your view, and beyond it, the water can continue without change. The horizon is a limit of information, and it does not reveal whether the ocean is bounded by land far away or whether it continues around the globe. In the sky, a similar effect appears. Stars become fewer and fainter, and eventually the sky darkens and detail fades, and that thinning does not signal an edge in space. This is where the secondary anchor fits stars thin out and go dark, not because space ends, but because light and time impose limits. Visibility is not geometry. The fading of starlight tells us about distance and history, and it does not tell us whether space wraps around or extends forever. The question of topology lives at a deeper level, and it requires global reasoning rather than a visual cue. Cosmological observations constrain topology indirectly. They look for repeating patterns in the sky. They test whether light paths intersect in unexpected ways, and they search for signatures of a small closed universe. So far, no clear evidence of a small closed topology has appeared. But absence of evidence is not evidence of absence. The observable region may be too small to reveal the full structure, and a closed universe could be much larger than what we can see. Its closure could lie far beyond the horizon, so the lack of repetition in our data does not settle the question. This is why cosmology remains careful in its language. It does not declare infinity based on near flatness. Alone, it reports consistency with flat models. It leaves topology as an open question, constrained but not fixed, because horizons limit what can be measured directly. The important point for the root remains simple. Whether the universe is finite or infinite, it does not need an edge, and the absence of an edge is not a clue by itself about size. Topology replaces the idea of a boundary, and connection replaces containment. This also explains why the title holds together. A universe can have no edge because space may not include a boundary. It can still have horizons because information is limited by light and cosmic history, and these statements operate on different levels. When people ask which option is true, finite or infinite, they often expect a visual answer. They want to picture a shape, but physics offers constraints instead of pictures. It narrows possibilities without forcing a single image, because the evidence is limited and the models remain broad. That restraint is not weakness, it reflects the limits imposed by horizons themselves. We reason globally from local evidence, and we do not invent walls to fill gaps. The fading stars are a reminder of this discipline, because they vanish from view without signaling a boundary. As measurements improve, constraints will tighten. Some topologies may be ruled out, and others may remain viable, and none will require an edge. The question of finiteness will remain a question of connection, not of borders. So the final tension dissolves. Finite versus infinite is a question about global structure. No edge is a statement about the absence of boundaries. Horizons are statements about information, and keeping these categories apart keeps the picture coherent. With that, all the pieces are in place. No edge, still horizons beyond, not outside, and the conclusion can simply lock the root without adding a new idea. The story ends where it began, with a line that looks like a border, but behaves like a limit on light. We began with a line that looked like a boundary, a thin ring of pale light on a night ocean. From a distance, it felt decisive, as if it separated what is inside from what is not, and the mind treated it like the rim of an object. Up close, The meaning changed because the line was only where information became too faint to reach us. That difference is the key to the whole route. An edge is a boundary of space, a place where the arena itself would stop. A horizon is a boundary of information, a limit set by light time and expansion, and those are different kinds of statement. The universe can lose the first without losing the second. First, no edge. The universe does not need a rim the way an object needs a surface, and geometry allows space to be unbounded even if it is finite. Topology can close paths without drawing borders, so no wall is required for space to be complete. Second, still a horizon. Because signals travel at a finite speed and the universe has a finite age, observation must have a boundary, and that boundary is real even if space has no edge. The particle horizon marks the farthest past from which light has reached us so far, and it is a limit written by travel time, not by offense. The event horizon adds a future-facing limit. In an accelerating expansion, there can be regions whose signals sent today will never reach us, and this is not a claim about what exists. It is a claim about causal contact, about what can ever influence what. The Hubble radius looks like an edge because it compares recession speed with the speed of light. But it is a kinematic scale, not a wall, and it changes as the expansion rate changes. It can be crossed by light in the right expansion history, so it cannot serve as a final border. The cosmic microwave background looks like a shell around us, but it is not a surface in space. It is light from a time when the universe became transparent, and its sphere is a timestamp on our past light cone. It encloses us in appearance, not in reality. Third, beyond does not mean outside. Beyond the observable horizon means beyond what has reached us so far, and beyond the event horizon means beyond future communication. Outside the universe is a container phrase that may have no physical target, because the universe is not a thing placed inside a larger room. Maps can confuse this distinction if we forget what they represent. A cosmic map has a rim because data has a boundary, because signals have not arrived, and because time limits observation. A border on a map is often the end of knowledge, not the end of what exists. The question of finite versus infinite belongs to global structure. Curvature tells us how space behaves locally, and topology tells us how it is connected as a whole. A near flat does not force infinity. None of these possibilities require an edge, so the title stops being a paradox. The universe can have no edge while still having horizons, because horizons are real limits created by finite light speed and cosmic history. They do not become walls just because they draw circles on our diagrams. Return one last time to the night ocean. The sea does not stop where your sight stops, and the line you see is not a barrier in the water. It is the last light that can reach you. That is the final form of the idea that has guided everything here. Horizon is an information limit, not a wall. A map can have a rim because knowledge has a boundary, and the territory does not have to.